build out a mathematical expression. So we have multiple inputs here, A, B, C, and F, going into a mathematical expression that produces a single output, L. And this here is visualizing the forward pass. So the output of the forward pass is -8. That's the value. Now, what we'd like to do next is we'd like to run backpropagation. And in backpropagation, we are going to start here at the end, and we're going to reverse.
What's all this grad stuff? 1 second. What is it good for? Absolutely nothing. What is it good for? Absolutely nothing. So, gradic. Cool. Oh, 1 sec. Okay. Wait, why is this still saying grad? What's the deal? What's the deal? Hold on. Okay. Brum 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 dum 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 dum. Ah, right. Radicals, young radicals, radicals. Okay. But wait, it's saying 0. Alright, here's the saying like 2.01 whatever. Why? Okay, so if I change this. Okay, so it's fetching the grad thing from here. Okay, cool. Uh-huh. Right. So I got the class value thingy. Right. Okay. What's that not a thing? Right. Ooh. There we go. Testing. 1, 2, 3. Okay. So the class value object seems to just be, like, from what I've seen so far, from what I've understood so far, it's like um, until it's called, it won't actually be stored in memory, right? Um, but when it's called, the init thing, init, is going to tell whatever it is in the uh, hard drive or computer or whatever, um, that, hey, store this stuff alongside or with this thing. That's what I think the init is doing. And so when we see data, that's just another thing to be stored alongside the cost value, I think. Not entirely sure. Um, but okay, we don't need to know for sure right now how that works, even though obviously we despise abstractions. Um, so we have that init thing, we're doing that. Then we have the self thing. Um, hmm. Self thing. One second. Hmm. Label, I'm not sure what it's doing. I think label is just there probably for the graph. Full stop. Space. Self.prev. I think what self.prev is doing is somehow setting like testing 1 2 3, testing 1 2 3. What the hell? The self.prev thing, I'm not sure what it's doing. Full stop. And restart. Okay. The self.prev. Um, hmm. Okay. What the hell? The OP, I'm not sure what that's doing, period. I'm not sure what that's doing. period. Full stop.
So if you can start doing the holiday course first, open the holiday course, we will do some changes. And
The self.prev seems to somehow be setting the previous functions or some other functions as something which leads into the other ones. I'm not sure what's going on there. I think is that something to do with GraphWiz, or is that something that's required for the actual backpropagation or the neural network stuff? I'm not certain. I experimented a little bit with seeing like, okay, if I change the word grad into something else, what happens? So far, it's not conclusive. It seems that when I change grad to like gradic, then it didn't work as it would have before. Full stop. I'll try out grad again and see what happens. Yeah, I'm not entirely sure about this. Full stop. Full stop. Okay, label. Okay, label I think is pretty obvious. It's literally just labeling a value. So like we have the E, C, D, etc.
yes, that will be division for past exam test and revision of past paper. Papers and correction and remaining topics.
there be light. Okay. So wrapper is just okay. Removing that part. That's not important. So add is just okay. I don't know why it was. Can't we just do normal addition? Right. That's the thing to try out. Like next time. So like when you're trying like pure Python, and JavaScript and stuff. Because I don't know why you need that thing there. Like I'm sure Python has like addition, right? Like yeah, it definitely does. It'll be like some class or something nonsense. Like okay. The itself. Okay. Let's see. Alright, so we're doing that now because
Yeah. Did you guys manage to do the water thing?
okay.
Still there is leak?
No, it's not leak, but
Okay. Now
Okay,
why
no
is
problem.
that
That we
happening?
don't know. That water meter thing I had said you.
Okay.
Okay. Okay. It is in that anyway, but I need to find out water meter serial number. Okay. Don't worry. I'm going to call them today. Okay.
So -2, 4, all that stuff. Okay. Right, it's drawn a bit differently, but that's fine. Why do we not have a grad here? Wait, okay, 1 second.
So we have multiple inputs here, A, B, C, and F, going into a mathematical expression that produces a single output, L. And this here is visualizing the forward pass. So the output of the forward pass is -8. That's the value. Now, what we'd like to do.
Okay, and to be clear, what exactly do we mean by forward pass? So what's literally happening here? So we're having a value called A, which we've defined to have 2. Then we've defined a value B, and this value is -3. Then we define a value C, which has 10. And we define the value E. And we define E to be the value of A times B. Okay. Then we define the value D, and define the value of D to what is that? A value? Anyways, whatever. Variable, whatever. A thing called D, and for that thing called D, what? I'm not gonna get that pedantic. Okay. So the thing which called D, I guess variable, whatever. The saying is going to equal value of that is going to be E plus C. Okay. So then I guess that's what we're saying, and then we have F. It's going to be D times F. So it goes from A, then into E, and then into D, and then into L. So boom, 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 boom. Okay, that's what we're calling a forward pass, just a series of calculations. So if I just say like 2, like if I say like, A equals 2, and then like +4, +9, -12, +8, whatever, like, is forward pass literally just a series of calculations? Is that literally just what it is? Um, calculations. Like if I say a equals 12, and then I say a plus b then equals c, and then I say that c minus d equals e, and then I say that e times f equals g. Is that a forward pass? What the hell is this? looks okay. Nope. Okay. How hard would it be to make this? Just deploy anything. I don't need the rest, just like. Okay. But you can change it. That's so cool. That's so cool. Wow, and you can just. That's so crazy. Wow. That's incredible. Okay. Oh, that's so cool. Okay. Oh, whoa. Okay. Alright. Now how do I undo that stuff? Bum, 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 bum. Okay. I mean, I'm pretty impressed. Okay, right. So we got this. Bam. Okay, so we have the weights. We got the weights. Okay, how do it's just a set. Okay. Right. Okay. So we got. Mm-hmm. One. -1, 0. 1. 0. Okay, don't have a lot of time. And 0 and 1. 0, 1, 1. So bias meaning, what does that mean? So what are you going to be doing to that? So any more multiplying by the weights. Okay. And then add the bias. Okay. How do you multiply by matrices again? Yep, remember that. But okay, but what about? Ah, wait. Okay, hold on a second. So that plus this plus. Wait. So, bum 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 done. 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 Okay, right. All right, that makes sense now. Okay. Okay, so we go bam bum 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 down. Bum 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 down. Bum 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 down. Right. Why is this how it works?
This you bring here, and that you bring here. But we have written here, this goes here. Because we are giving regular measure. But all the topics in the above sections are clear. Yes, so that's what here. This one we bring here. And this what we giving more detail what we're doing goes here. And because everywhere else they're giving detail here. That's why bring this one here, and here you're going to put only GCSE. So you know this the word GCSE. Yeah. Now you bring this one. And type a GCSE, year 10, year 11. Year 10, year 11. Does it make sense now?
Okay, right. So you have some products. So how much is sold in 14 stores? Okay. Total revenue of each store. Okay, hold on a second. Oh wait. Okay, so in store, so each right, so each row and column represents like an axis on some graph or something. Right? Okay, so like right, okay, so these could be like different stores. And okay. Okay. So then saying that store one has those three products. It has 13 of those and has 8 of those and 6 of those. Okay, so then that's like, oh, okay, so match. Okay, okay. Right. And so what would, okay, so here in the first one, we're representing the price of each product, and here So price of each product multiplied by, okay, so it's like the price of each product multiplied by how much of each product. Oh, okay. So if you have so here we're displaying like how much the store how much of each how much each store has of the product, and then now we're using a price to work out how much um okay. So now we use the price to work out how much each store makes in total from those products. Okay, or like how much, what a value, cost, etc. there is um, in each of those products, and it could also be like profit or something. Okay, and if this one had like more rows, then that might represent like different prices in each product, in different prices in different stores. So maybe like in one region, uh, some stores make more money or less money, something from a product. And oh yeah, so there would be four stores. Yeah, and so yeah, of course. So there'd be four stores, and so it'll still work because you'd just be doing matrix multiplication. Okay, right. So now when we're doing like neural networks, right? Um, so each one of those, like, what is that? We have like 512, whatever. What's the D model again? Um, actually, one sec.
Once you fix it, convert it into PDF. Save one as a Word also, and one in PDF. We'll be sending to the customer PDF. So that it's not getting here and there.
Okay, so there's 512. Okay, so what's actually doing here? Hmm. 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 It's something to do with like. Okay, so it's n. Okay, so n is the number of tokens in the sequence. Okay, hold on a sec. Right. So each token is like matched to an embedding. Ah, right. Okay, so D model is okay. Okay, so hold on a second. Uh huh. Ah, right. There we go. There we go. That's the one. That's the one. Right. Okay. So, yes, 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 yes. And so you have some sequence. Right. And if those sequence was more, then you just have more of both. Okay. Um. Bum 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 bum. Okay. One second. Okay. Anyway, so this is so yeah. Ba 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 ba. Bam. Mm-hmm. Okay, wait. So what are you actually doing there? Okay. So when you're doing that, what are you actually doing? So you are saying, okay, so you're taking all of those things which I'm making up. Okay, right. So when you do that, you're gonna have. Okay, so let's say. Okay, let's suppose you're like for each character, each one of you things, you've taken it up and represented it with the 512. You take it up with 512, and then you're getting all of that information, I guess. Okay, so then you're getting all of that information, bam, into one number. So you have like one solidified block saying what this number is about, what this character is about. Okay, I think that's kind of what that is. And then bam, another one, and then bam, another one, bam, another one, bam, another one. Okay, okay, I think that makes sense. Uh, right. Hey, Ayush, or someone else who, if you happen to be watching like this part, uh, and you know like I'm wrong in some way or something, or I'm missing some stuff, please tell me. Yeah, like tell me if I'm just like wrong or missing something and stuff. I want to know. Pog. All right, back to micrograd. Right, that's actually um cool, cool, cool. That was a fun little detour. I'm feeling pretty satisfied with that actually. That's I don't think I need to. Let's see. Okay, so let's see here. So what we actually do now. So forward pass. Yeah, I don't think it's actually calling that a forward pass. Um, da, 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 da. Right, so let's keep going because we don't have that much time left. Um, come on, buddy. Buddy. Come on. Okay. Right.
Next, if we'd like to run back propagation and get back,
Whoa, wait, buddy.
and we can do this forward pass and build out a mathematical expression. So we have multiple inputs here, A, B, C, and F, going into a mathematical.
Whoa, buddy. Okay, so you are coding that a forward pass. Come on. Okay. Borders, what's up with that? Right. Okay, so I'm right and you just made it. No, shut up. Shut up. Shut up. Oh my god. Oh. Jesus Christ. I hate this so much. Like, shut up. Shut up. Jesus Christ. Fucking hell. Okay.
Expression that produces a single output L. And this here is visualizing the forward pass. So the output of the forward pass is -8. That's the value. Now, what we'd like to do next is we'd like to run backpropagation. And in backpropagation, we are going to start here at the end, and we're going to reverse and calculate the gradient along all these intermediate values. And really what we're computing is for every single value here, we're going to compute the derivative of that node with respect to L. So the derivative of L with respect to L is just 1. And then we're going to derive, what is the derivative of L with respect to F, with respect to D, with respect to C, with respect to E, with respect to B, and with respect to A. And in a neural network setting, you'd be very interested in the derivative of basically this loss function, L, with respect to the weights of a neural network. And here, of course, we have just these variables A, B, C, and F, but some of these will eventually represent the weights of a neural net. And so we'll need to know how those weights are impacting the loss function. So we'll be interested basically in the derivative of the output with respect to some of its leaf nodes. And those leaf nodes will be the weights of the neural net. And the other leaf nodes, of course, will be the data itself. But usually we will not want or use the derivative of the loss function with respect to data because the data is fixed, but the weights will be iterated on using the gradient information. So next we are going to create a variable inside the value class that maintains the derivative of L with respect to that value. And we will call this variable grad. So there's a using the gradient information. So next we are going to create a variable inside the value class that maintains the derivative of L with respect.
Okay. So grad is about maintaining the okay.
Inside the value class that maintains the derivative of L with respect to that value. And we will call this variable grad. So there's a .data and there's a self-left grad, and initially it will be 0. And remember that 0 is basically means no effect. So at initialization, we're assuming that every value does not affect the output, right? Because if the gradient is 0, that means that changing this variable is not changing the loss function. So by default, we assume that the gradient is 0, and then now that we have grad and it's 0.0, we are going to be able to visualize it here after data. So here grad is 0.4f, and this will be grad. And now we are going to be showing both the data and the grad initialized at 0.
Okay.
And we are just about getting ready to calculate the backpropagation.
Okay.
And of course, this grad, again, as I mentioned, is representing the derivative of the output.
So
In this case, L, with respect to this value. So with respect to, this is the derivative of L with respect to F, with respect to D, and so on. So let's now fill in those gradients and actually do backpropagation manually. So let's start filling in these gradients and start all the way at the end, as I mentioned here. First, we're interested to fill in this gradient here. So what is the derivative of L with respect to L? In other words, if I change L by a tiny amount of h, how much does L change? It changes by h. So it's proportional, and therefore the derivative will be 1. We can, of course, measure these or estimate these numerical gradients numerically, just like we've seen before. So if I take this expression and I create a def LOL function here and put this here. Now, the reason I'm creating a gating function LOL here is because I don't want to pollute or mess up the global scope here. This is just kind of like a little staging area. And as you know, in Python, all of these will be local variables to this function. So I'm not changing any of the global scope here. So here, L1 will be L. And then copy pasting this expression. We're going to add a small amount h in, for example, a. Right? And this would be measuring the derivative of L with respect to a. So here, this will be L2. And then we want to print that derivative. So print L2 minus L1, which is how much L changed, and then normalize it by h. So this is the rise over 1. And we have to be careful because L is a value node, so we actually want its data. So that these are floats divided by h. And this should print the derivative of L with respect to a. So we actually want its data. So that these are floats divided by h. And this should print the derivative of L with respect to a, because a is the one that we bumped a little bit by h. So what is the derivative of L with respect to a? It's 6. Okay, and obviously, if we change L by h, then that would be here effectively. This looks really awkward, but changing L by h, you see the derivative here is 1. It's kind of like the base case of what we are doing here. So basically, we can come here, and we can manually set L.grad to 1. This is our manual backpropagation. L.grad is 1, and let's redraw. And we'll see that we filled in grad is 1 for L. We're now going to continue the backpropagation. So let's here look at the derivatives of L with respect to D and F. Let's do D first. So what we are interested in, if I can read the turn on here, is we'd like to know, basically we have that L is D times F, and we'd like to know what is dl by dd. What is that? And if you know your calculus, L is d times F, so what is dl by dd? It would be F. And if you don't believe me, we can also just derive it because the proof would be fairly straightforward. We go to the definition of the derivative, which is f of x plus h minus f of x divide.
1 second. What's going on here, buddy? Yeah, buddy. One sec. Let's see what to do now.
This looks really awkward, but changing L by h, you see the derivative here is 1. That's kind of like the base case of what we are doing here. So basically, we can come here, and we can manually set L.grad to 1. This is our manual backpropagation. L.grad is 1, and let's redraw. And we'll see that we filled in grad is 1 for L. We're now going to continue the backpropagation. So let's here look at the derivatives of L with respect to D and F. Let's do D first. So what we are interested in, like,
oh, okay, because then we add that thing. This thing doesn't have value. Shame. That's so stupid.
we'd like to know, basically we have that L is D times F, and we'd like to know what is dl by dd. What is that? And if you know your calculus, L is D times F, so what is dl by dd? It would be F. And if you don't believe me, we can also just derive it because the proof would be fairly straightforward. We go to the definition of the derivative, which is f of x plus h minus f of x divide h. As a limit, limit of h goes to 0 of this kind of expression. So when we have L is D times F, then increasing D by H would give us the output of D plus H times F. That's basically f of x plus H, right? Minus D times F.
Okay.
And then divide H.
Right.
And symbolically expanding out here, we would have basically D times F plus H times F minus D times F divide H.
Oh, yeah. Oh, so HF. Oh, yeah, cool.
And then you see how the df minus
Good
df
stuff.
cancels,
I like
so
it.
you're left with H times F. Divide H,
Good stuff.
which is F. So in the limit as H goes to 0 of, derivative definition, we just get F in the case of D times F. So symmetrically, dl by df will just be D. So what we have is that f dot grad we see now is just the value of D, which is 4. Okay. Minus D times F. And then divide H. And symbolically expanding out here, we would have basically D times F plus H times F minus D times F divide H. And then you see how the df minus df cancels, so you're left with H times F divide H, which is F. So in the limit as H goes to 0 of, derivative definition, we just get F in the case of D times F. So symmetrically, dl by df will just be D. So what we have is that f dot grad we see now is just the value of D, which is 4.
Cool.
And we see that
Okay, I'm convinced. What? What? Why does that work? Oh, because that's inside the thing. Okay. Wait. Oh, there's some Python bullshit going on. What if you just make H a value object? Bam. Okay, there we go. Right. So D. Bam. Okay.
D dot.
Let's do it for these. So E, it's gonna be. E is gonna be. Yappa tappa dee. Yahoo! So -2. You get a -2. You get a -2. It's gonna be an error. Yes, nice. Good stuff. Good. Oh, that's a -4. So, and that's curious. Oops. Does that work? Oh, that does work. Interesting. Right.
Grad is just the value of f. And so the value of f is -2. So we'll set those manually. Let me erase this markdown node, and then let's redraw what we have. Okay. And let's just make sure that these are correct. So we seem to think that dl by dt is -2. So let's double check. Let me erase this plus h from before. And now we want the derivative with respect to f. So let's just come here when I create f, and let's do a plus h here. And this should print the derivative of l with respect to f. So we expect to see 4. Yeah, and this is 4 up to floating point funkiness. And then dl by dd should be f, which is -2. Grad is -2. So if we again come here and we change dd, d dot data plus equals h right here. So we expect, so we've added a little h, and then we see how L changed. And we expect to print -2. There we go. So we numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results. And then numerical gradient is just, estimating it using, and we expect to print -2. There we go. So we numerically verified. What we're doing here is kind of like an inline gradient check. Gradient check is when we are deriving this like backpropagation and getting the derivative with respect to all the intermediate results. And And then numerical gradient is just, estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to
बाथरूम में हो गया अब ये वो
Oh wait, one sec. One sec. Oh wait, I should open that up somewhere else. Just went to go put some medicine on. I'll do the back propagating, back propagating, back propagating. Da 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 da. Yeah. Cool. Do you reckon the human is a physical thing? Oh, damn. I am. Alright. Okay. Jesus Christ. Okay. Hurry up. Hurry up. Hurry up.
Estimating it using small step size. Now we're getting to the crux of backpropagation. So this will be the most important node to understand, because if you understand the gradient for this node, you understand all of backpropagation and all of training of neural nets, basically. So we need to derive DL and all of training of neural nets, basically. So we need to derive DL by DC. In other words, the derivative.
I hate that word, basically. Because it always means not actually.
Of L with respect
Almost
to
always.
C.
In this
Because we
context.
computed all these other gradients already. Now we're coming here and we're continuing the backpropagation manually. So we want dl by dc, and then we'll also derive dl by de. Now here's the problem. How do we derive dl by dc? We actually know the derivative of L with respect to D. So we know how L is sensitive to D. But how is L sensitive to C? So if we wiggle C, how does that impact L through D? So we know dl by dc.
Chain rule.
And we also here know how C impacts D. And so just very intuitively, if you know the impact that C is having on D, and the impact that D is having on L, then you should be able to somehow put that information together to figure out how C impacts L. And indeed, this is what we can actually do. So in particular, we know, just concentrating on D first, let's look at what is the derivative basically of D with respect to C. So in other words, what is dd by dc? So here we know that D is C times C plus E. That's what we know. And now we're interested in dd by dc. If you just know your calculus again and you remember, then differentiating C plus E with respect to C, you know that gives you 1 and 0. And we can also go back to the basics and derive this. Because again, we can go to our interest in dd by dc. If you just know your calculus again and you remember, then differentiating C plus E with respect to C, you know that gives you 1 and 0. And we can also go back to the basics and derive this. Because again, we can go to our f of x plus h minus f of x divided by h as the definition of a derivative as h goes to 0. And so here, focusing on C and its effect on D, we can basically do the f of x plus h will be C is incremented by h plus E. That's the first evaluation of our function, minus C plus E. And then divide h. And so what is this? Just expanding this out, this will be C plus H plus C minus E divide H. And then you see here how C minus. C cancels, E minus E cancels, we're left with H over H, which is 1 plus 0. And so, by symmetry also, D by D E will be 1 plus 0 as well. So basically the derivative of a sum expression is very simple, and this is the local derivative. So I call this the local derivative because we have the final output value all the way at the end of this graph. And we're now like a small node here, and this is a little plus node. And the little plus node doesn't know anything about the rest of the graph that it's embedded in. All it knows is that it did a plus. It took a C and an E node, and the little plus node doesn't know anything about the rest of the graph that it's embedded in. All it knows is that it did a plus. It took a C and an E, added them, and created a D. And this plus node also knows the local influence of C on D, or rather the derivative of D with respect to C. And it also knows the derivative of D with respect to E. But that's not what we want. That's just a local derivative. What we actually want is dL by dC. And L is here just one step away. But in the general case, this little plus node can be embedded in like a massive graph. So again, we know how L impacts D, and now we know how C and E impact D. How do we put that information together to write dL by dC? And the answer, of course, is the chain rule in calculus.
The chain rule is cool.
I took the chain rule here from Wikipedia, and I'm going to go through this very briefly. So chain rule, Wikipedia sometimes can be very confusing, and calculus can be very confusing. Like, this is the way I learned chain rule, and it was very confusing. Like, what is happening? It's just complicated. So I like this expression much better. If a variable z depends on a variable
What's the
y,
deal?
which itself depends on the variable x, then z depends on x as well, obviously, through the intermediate variable y. And in this case, the chain rule is expressed
Thank you,
as, if
StackWest.
you want dz by dx, then you take the dz by dy and you multiply it by dy by dx. The chain rule fundamentally is telling you how we chain these derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. And there's a nice little intuitive explanation here, which I also think is kind of cute. The chain rule states that knowing the instantaneous rate of change of z with respect to y, and y relative to x allows one to calculate the instantaneous rate of change of z. So that's real. To differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. Derivatives together correctly. So to differentiate through a function composition, we have to apply a multiplication of those derivatives. So that's really what chain rule is telling us. And there's a nice little intuitive explanation here, which I also think is kind of cute. The chain rule states that knowing the instantaneous rate of change of z with respect to y, and y relative to x allows one to calculate the instantaneous rate of change of z relative to x as a product of those two rates of change. Simple. So that's really what chain rule is telling us. And there's a nice little intuitive explanation here, which I also think is kind of cute. The chain rule states that knowing the instantaneous rate of change of z with respect to y, and y relative to x allows one to calculate the instantaneous rate of change of z relative to x as a product of those two rates of change. Simply the product of those two. So here's a good one. If a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then the car travels 2 times 4, 8 times as fast as a man. And so this makes it very clear that the correct thing to do sort of is to multiply. So car is twice as fast as a bicycle, and bicycle is 4 times as fast as man.
Nice.
So the car will be 8 times as fast as the man. And so we can take these intermediate rates of change, if you will, and multiply them together. And that justifies the chain rule intuitively. So have a look at chain rule, but here, really what it means for us is there's a very simple recipe for deriving what we want, which is dL by dC. And what we have so far is we know one,
So like, if I'm like, if you're like the emperor and you got like your goblins, and the goblin king told you like, yo, there's 20 of us. It's a small kingdom, all right, calm down. The goblin king says like, there's 20 of us, and those pesky elves, there's like, they have 10 times more of them than there's like than there is of us. And then like the elf king is like I haven't counted like how many of us there are because I'm a dick. But I know like for each one of us, there's at least like 3 orcs, right? I don't know. I'll leave it up to you to figure out how they know that. Um, um, right? So you know there's like that many orcs, and the orc king is like, um, "Brr, no, I haven't counted how many of us there are because I can't count that high. Um, but I know that for every one of us, there's 2 dwarves because we all have a hammer and a shield, and we each one of us has one dwarf who makes us a hammer and one dwarf who makes us a shield. Yeah, and I know all of the ones living in that tunnel, they are all working with us. There's nobody else, right? And so then you can use that chain rule there to calculate how many orcs there are, how many dwarfs there are, because the goblin fella told you how many goblins there are. Yeah, chain rule. And then use the chains to bind them all up to a nice little box.
And we know
Trains.
what is the impact of d on L. So we know dl by dt, the derivative of L with respect to dt. We know that that's negative 2.
Trains.
And now, because of this local reasoning that we've done here, we know dd by d.
Oh no, it was like a nasty bit at the end. Yeah, that's nasty. Not pixie lot nasty, that's just like straight nasty.
Because of this local reasoning that we've done here, we know dd by dc. So how does c impact d? And in particular, this is a plus node, so the local derivative is
Trains.
1.0. It's very simple. C. So how does c impact d? And in particular, this is a plus node, so the local
Trains.
derivative is simply 1.0. It's very simple. And so the chain rule tells us that dl by dc, going through this intermediate variable, will just be simply dl by dd times dD by dC. That's chain rule. So this is identical to what's happening here. Except,
Identical.
Z is RL, Y is RD, and X is RC. So we'll literally just have to multiply this and B.
Don't be a penis. Don't be a penis. Don't be a penis. Come on, it's a small task. Don't be a penis. Come on, get up. There you go. That's a good GitHub. Hey. I see. Okay, let's see.
Because these local derivatives, like dd by dc, are just one, we basically just copy over dl by dd, because this is just times 1. So what is it? So because dl by dd is -2, what is dl by dc? Well, it's the local gradient 1.0 times dl by dt, which is -2. So literally, with a plus.
Oh, whoops. Okay, that was a mistake.
these local derivatives, like dt by dc, are just 1, we basically just copy over dl by dd, because this is just times 1. So what is it? So because dl by dd is -2, what is dl by dc? Well, it's the local gradient 1.0 times dl by dt, which is -2. So literally, what a plus node does, you can look at it that way, is it literally just routes the gradient, because the plus node's local derivatives are just 1. And so in the chain rule, 1 times dl by dd is
Just dl by dd.
is just dl by dt. And so that derivative just gets routed to both c and to e in this case.
Okay.
So basically, we have that micrograd, or let's start with c, since that's the one we looked at, is -2 times 1, -2. And in the same way, by symmetry,
nice.
e that grad will be -2. That's the
Okay,
claim.
cool.
So we can set those.
Okay.
We can redraw. And you see how we just assign -2, -2? So this backpropagating signal, which is carrying the information of like what is the derivative of L with respect to holding intermediate nodes, we can imagine it almost like flowing backwards through the graph, and a plus node will simply distribute the derivative to all the leaf nodes, to all the children nodes of it. So this is the claim, and now let's verify it. So let me remove the plus h here from before, and now instead what we're going to do is we want to increment c. So c dot data will be incremented by h, and when I run this, we expect to see -2.
Pogu.
And then of course for e, so e dot data plus equals h, and we expect to see -2.
Yes.
So those are the derivatives of these internal nodes. And now we're going to recurse our way backwards again. And we're again going to apply the chain rule. So here we go, our second application of chain rule, and we will apply it all.
A second application of chain rule has hit the tutorial.
The way through the graph. We just happen to only have one more node remaining. We have that dl by de, as we have just calculated, is -2. So we know that. So we know the derivative of L with respect to e. And now we want dl by dA, right? And the chain rule is telling us that that's just dl by dA,
and then de by dA,
-2, times the local gradient. So what is the local gradient? Basically dE by dA. We have to look at that. So I'm a little times node inside a massive graph, and I only know that I did A times B, and I produced an E. So now what is dE by dA and dE by dB? That's the only thing that I sort of know about. That's my local gradient. So because we have that E is A times B, we're asking what is dE by dA? And of course we just did that here. We had a times, so I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is -3.0. So basically we have times
No, don't disconnect me.
So I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is negative 3.0. So basically we have that dl by dA. Well, let me just do it right here. We have that A dot grad, and we are applying chain rule here, is dl by dE, which we see here is negative 2, times, what is dE by dA? It's the value of B, which is negative 3. That's it. And then we have B dot grad, is again dl by dE, which is negative 2, just the same way, times, what is dE by dB? Is the value of A, which is 2.0. That's the value of A.
Yeah, but
So these are our claimed derivatives. Let's redraw. And we see here that A dot grad turns out to be 6 because that is negative 2 times negative 3. And B dot grad is negative 4 times, is negative 2 times 2, which is negative 4. So those are our claims. Let's delete this and let's verify them. We have A here, A dot data plus equals H. So the claim is that A dot grad is 6. Let's verify 6. And we have B dot data plus equals H. So nudging B by H and looking at what happens, we claim it's negative 4. And indeed, it's negative 4, plus minus, again, float, oddness. That's it. That was the manual backpropagation all the way from here to all the leaf nodes. And we've done it piece by piece. And really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output. And then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always.
yeah.
So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is. It's just a recursive application of chain rule backwards through the computation graph.
Fantastic.
Let's see this power in action, just very briefly. What we're going to do is we're
come
going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want A dot data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this for B, but also for B. Or we want A dot data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So A should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this for B, but also for B.
Oh, okay. So in the direction means like.
also for C, also for F. Those are leaf nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively, so it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell exactly. And we have to rewrite it, usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively, so it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell. Leaf nodes, which we usually have control over. And if we nudge in also for C, also for F, those are leaf nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively, so it should become less negative. It should go up to say negative 6 or something like that. It's hard to tell exactly. And we have to rewrite the forward pass. So let me just do that here.
Whoa! What's the deal, Jose? Okay. Okay, so wait, that's yeah, because that's put dun, dun, then dun, then dun. That's the forward pass. Okay. Ah. Okay. Okay.
This would be forward pass. F would be unchanged.
Hold a second. Hold on. Hold the fuck on. Hold the fuck on. So A, B, C, and F. Okay. Oh. Actually, okay, not much time. Really, not much time. Actually, I'm almost halfway through. Okay. How long am I taking? Jesus Christ. Okay.
This is effectively the forward pass. And now if we print L.data.
Okay. Right. Okay. So it's C. F. So E equals A sub B. A sub Z. A sub Z. A sub Z. Z equals E plus C. Else equals Z times F times S. Okay. So print. So print L dot data. Okay.
We expect because we nudged all the values, all the inputs in the direction of gradient, we expected a less negative L. We expected to go up. So maybe it's -6 or so. Let's see what happens. Okay, -7. And this is basically one step of an optimization that we'll end up running. And really, this gradient just gives us some power because we know how to influence the power. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more example of manual backpropagation using a bit more complex and useful example. We are going to backpropagate through a neuron. So we want to eventually build out neural networks. And in the simplest case, these are multi-layer perceptrons, as they're called. So this is a 2-layer neural net. And it's got these hidden layers made up of neurons. And these neurons are fully connected to each other. Now, biologically, neurons are very complicated devices, but we have very simple mathematical models of them. And so this is a very simple mathematical model of a neuron. You have some inputs, x's, and then you have these synapses that have weights on them. So the W's are weights. And then the synapse interacts with.
And so the weight just means a thing being multiplied, right? Yeah, the weight is literally just the thing in the matrix. Yeah, the number in the matrix which is multiplying the input, and then the bias is going to be added on. Right, yeah, of course. Yeah. They should call it M for multiplying.
The input to this neuron synapses that have weights on them. So the W's are weights. And then the synapse interacts with the input to this neuron multiplicatively. So what flows to the cell body of this neuron is W times X. But there's multiple inputs, so there's many W times X's flowing into the cell body. The cell body then has also some bias. So this is kind of like the innate sort of trigger happiness of this neuron. So this bias can make it a bit more trigger happy or a bit less trigger happy, regardless of the input. But basically, we're taking all the W times X of all the inputs, adding the bias, and then we take it through an activation function. And this activation function is usually some kind of a squashing function, like a sigmoid or a tanh or something like that. So as an example, we're going to use the tanh in this example. NumPy has a np.tanh, so we can call it on a range, and we can plot it. This is the tanh function, and you see that the inputs, as they come in, get squashed on the y coordinate here. So right at 0, we're going to get exactly 0. And then as you go.
So a range is just like, so setting like, okay, give me like the sort of values between this one and that one, and then this is setting like the increments. So I set like the increment to be like 10 or whatever. Oh, whoops. Yeah, so you get nothing, right? If I set the increment, how does that work? Nice. 0.8. That's going to give an error, right? Nice. That should be like. Interesting. Huh. What if it's like minus 9? Minus 9. Okay. But do they have value in there? Yo, they got the cost in there. Okay, cool.
Or positive in the input, then you'll see
Why
that the
the
function will
squashing?
only go up to 1 and then plateau out. And so if you pass in very positive inputs, we're going to cap it smoothly at 1. And on the negative side, we're going to cap it smoothly to -1. So that's 10H. And that's the squashing function or an activation function. And what comes out of this neuron is just the activation function applied to the dot product of the weights and the inputs. So let's write.
Gotcha.
One out. I'm going to do copy paste because I don't want to type too much. But okay, so here we have the input x1, just the activation function applied to the dot product of the weights and the inputs. So let's write one out. copy paste because I don't want to type too much. But okay, so here we have the inputs, x1, x2. So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron, weights W1, W2. And these weights, again, are the synaptic strengths for each input. And this is the bias of the neuron, B. And now what we want to do is, according to this model, we need to multiply x1 times W1 and x2 times W2. And then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 W1 plus x2 W2 plus B. And these are multiplied here. Except I'm doing it in small steps so that we actually have pointers to all these intermediate nodes. So we have x1 W1 variable, x times x2 W2 variable, and I'm also labeling them. So N is now the cell body raw activation without the activation function for now. And this should be enough to basically plot it. So draw dot of N gives us x1 times W1, x2 times W2 being added. Then the bias gets added on top of this. And this N is this sum. So we're now going to take it through an activation function. And let's say we use the 10H so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, is N dot 10H. Okay, but we haven't yet written. And let's say we use the 10H so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, being added. Then the bias gets added. So we have x1 W1 variable, x times x2 weights W1, W2. And these weights, again, are the synaptic strengths for each input. And this is the bias of the neuron.
Okay, so synaptic strings meaning like it's the thing we multiplied. Just say the thing we multiplied, right? It's the parts. It's like you have a matrix, which is like this grid of numbers, and it's part of a grid, which is multiplying. This is the multiplying part, right? And sure, he's talking about some abstract, big old concept, but it's multiplying. That's what it is. It's multiplying.
So let's write one out. I'm going to copy paste because I don't want to type too much. But okay, so here we have the inputs, x1, x2. So this is a two-dimensional.
Let's see, boy. Bam. Okay. Jesus Christ. Okay. Bam bam. Huh? One second. क्या हुआ? हाँ.
हेलो। हाँ भाभी, आपने लगाया? ना वो एक रूम वाला तो हो गया, वो बड़ी वाली विंडो और कौन सी लगी? नहीं मेरे को छोटा ही है। ये जैसे कपड़ा नहीं है। एक और काम है, वो उसका काम है, वो भी चीज ये बंदे हैं इसलिए ये आता है। सामने वाला रूम सामने है राइट? इधर ऑफिस से लेके जाओ मैं भी ऐसे ही करती हूँ क्योंकि तो बाथरूम में तो नहीं है मैं बाथरूम में नहीं ये ले जाऊंगी बाथरूम में रखता हूँ
What's this? Well. This don't know how to backcrop. Still got by the mats. Amazing. No, no. Okay, let's see. Okay.
Based because I don't want function or an activation function. And what comes out of this neuron is just the activation function applied to the dot product of the weights and the inputs. So let's write one out. I'm going to copy paste because I don't want to type too much. But okay, so here we have the inputs, x1, x2. So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron, weights W1, W2. And these weights, again, are the
Okay. That's fine. Bam, 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 ba-dam, bam, 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 ba-dam.
So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron, weights W1, W2. And these weights, again, are the synaptic strengths for each input. And this is the bias of the neuron, B. And now what we want to do is, according to this model, we need to multiply x1 times W1 and x2 times W2 and then we need to add bias on top of it. According to this model, we need to multiply for each input. And this is the bias of the neuron, B. And now what we want to do is, according to this model, we need to multiply x1 times w1 and x2 times w2. And then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 w1 plus x2 w2 plus b. And these are multiplied here. Except I'm doing it in small steps.
Bam 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 bam. Okay. Oh wait, this is dumb. I should just do this. Can I just? Oh, I guess I'll just do that thing. I guess. Whatever. So minus 3.0, 1.0, and bias of the neuron equals right. Da-dum. Da-dum ba-dum 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 ba-dum. It's a really stupid thing to call it, I guess. What does the semicolon mean? I don't know. Something like linking things together. Okay. Oh my god. Oh my god. It even has a watermark. Jesus Christ, oh my god. Oh, I hate that. Okay. X1, W1, X2, W2 equals X. God damn it. Yeah. And two. One second. What? Okay, that's misleading. Okay, that's very misleading. It should not be called that. Instead, it should be called like.
So that we actually have pointers to all these intermediate nodes. So we have x1 W1 variable, x times x, and then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 W1 plus x2 W2 plus b, and these are multiplied here. Except I'm doing it in small steps so that we actually have pointers to all these intermediate nodes. So we have x1 W1 variable.
What's a pointer?
X2 W2.
What's a pointer? What's a point?
So n is now the cell body raw activation without the activation function for now. And this should be enough to basically plot it. So drawn out of n gives us x1 times w1, x2 times w2 being added, and the bias gets added on top of this, and this n is this sum. So we're now going to take, gives us x1 times w1, x2 times w2 being added, and the bias gets added on top of this, and this n is this sum. So we're now going to take it through an activation function, and let's say we use the 10H, so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, is n dot 10H. Okay, but we haven't yet written the 10H. Now, the reason that we need to implement another 10H function here is that 10H is a hyperbolic function, and we've only so far implemented a plus and a times, and you can't make a 10H out of just pluses and times. Right. You also need exponentiation. So 10H is this kind of a formula here. You can use either one of these, and you see that there is exponentiation involved, which we have not implemented yet for our low value node here. So we're not going to be able to produce 10H yet, and we have to go back up and.
Oh, we also need to divide. So
you can use either one of these, and you see that there is exponentiation involved, which we have not implemented yet for our low value node here. So we're not going to be able to produce 10H yet, and we have to go back up and implement something.
And yet we'd also need to divide.
Now, one option here is we could actually implement exponentiation, right? Oh. And we could return these x of the value instead of a 10H of the value. Because if we have x, then we have everything else that we need. So because we know how to add and we know how to add and we know how to multiply. So we'd be able to create 10H if we knew how to X. But for the purposes of this example, I specifically wanted to show you that we don't necessarily need to have the most atomic pieces in this value object. We can actually create functions at arbitrary points of abstraction. They can be complicated functions, or they can be also very, very simple functions like a plus. And it's totally up to us. The only thing that matters is that we know how to differentiate through any one function. So we take some inputs and we make an output. The only thing that matters can be arbitrarily complex function, as long as you know how to create the local derivative. If you know the local derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. We're just going to directly implement 10H. So let's do that. Get 10H, and then out will be a value of, and we need this expression here. So let me actually copy paste. Let's grab n, which is a delta theta, and then this, I believe, is the 10H. Math.x of
How's it? Wait, okay. Oh.
Derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. We're just going to directly implement 10H. So let's do that. Get 10H, and then out will be a value of, and we need this expression here. So let me actually copy paste. Let's grab n, which is a delta theta, and then this, I believe, is the 10H. Math.x of 2, n minus 1 over 2n plus 1. Maybe I can call this x.
Well, wait, okay, so we can just pop the whole thing in there. Can we just do that? So we can just so we could chuck sigmoid or something in here. We could just make it up out of exponents and stuff. I guess because it already exists, whatever, in NumPy. Oh wait, this exponents already exists in Python. Okay, what? That's crazy. Python has exponents. All right. I mean, I guess I don't know if it's crazy, but it feels crazy to me. But I guess it's mathematical function, so it's Will Smith. He's America's dad.
Just look at it match exactly. Okay, and now this will be t, and children of this node, there's just one child, and I'm wrapping it in a tuple. So this is a tuple of one object, just self, and here the and children of this node, there's just one child, and I'm wrapping it in a tuple. So this is a tuple of one object, just self, and here the, maybe I can call this x, just so that it matches exactly. Okay, and now this will be t, and children of this node, there's just one child, and I'm wrapping it in a tuple. So this is a tuple of one. that x of 2, and
Okay.
n minus 1 over 2n plus 1. Maybe I can call this s. Just so that it matches exactly. Okay. And now this will be t.
Okay, wait. Let's see. Should I pause or keep going? Meeting at 4. Tell you what, I'll judge it at 3. Okay, I'll make a judgment call at 3. If at 3 o'clock I'm not already 2 hours in, then I'll pause and I'll go. Okay, so
Maybe I can call this s.
Okay.
Just so that it matches exactly. Okay. And now this will be t. And children of this node, there's just one child. And children of this node, there's just one child. And I'm wrapping it in a tuple. So this is a tuple of one object, just self. And here, the name of this operation will be 10h. And we're going to return. Okay. So now values should be implementing 10h. And now if we scroll all the way down here,
okay. So math not exponent.
and here, the name of this operation will be 10h.
Okay.
And we're going to return.
Okay. Cool. 30.
So now values should be implementing 10h. And now we can scroll all the way down here, and we can actually do n.10h, and that's going to return the 10h output of n. And now we should be able to draw down output of n. Implementing 10.
Over 10 out.
So now values should be implementing 10h. And now we can scroll all the way down here, and we can actually do n.10h, and that's going to return the 10h output of n.
हाँ
माँ
गार्डन में क्या
गार्डन में तो नहीं दिख रहा है
नानी के बारे में नहीं है अम्मा नानी के बारे में नहीं है क्या डैड से पूछियो अगर उन्होंने लिया कि नहीं
And now we should be able to draw it out of O, not 10. So let's see how it works. There we go. And run through 10H to produce this output. So now 10H is a sort of our little micrograd supported node here as an operation. And as long as we know the derivative of 10H, then we'll be able to backpropagate through. Now let's see this 10H in action. Currently it's not squashing too much because the input to it is pretty low. So if the bias was increased to say 8, then we'll see that what's flowing into 10H now is 2. And 10H is squashing through 0.96. So we're already hitting the tail.
Okay, so there's actually no need for that though, because it's actually. Oh, right, draw dot. So I can just do draw dot O right there. Okay. Okay, see. Right, there's no need for it though.
Pretty low. So if the bias was increased to say 8, then we'll see that what's blowing into 10H now is 2. And 10H is squashing through 0.96. So we're already hitting the tail of this 10H. And it will sort of.
Okay. Right. Okay, pause this. What was that up there?